Hi everyone! Today let's talk about section 12.4, partial derivatives. Consider the function f of xy whose contour plot is shown in the figure on the right. Suppose you start at the point 1, 1, and you begin to move. What happens to the value of f of xy? The answer is it depends on which way you go, right? As you start moving in the positive x direction. So we're at the point 1, 1. So 1, 1 is right here. No? Okay. So 1, 1 is right here. So if we move in the positive x direction, what happened? You can see the numbers increases, right? So we have the function f increases. If we start to move in the positive y direction, what happened? Okay, so if we move to the positive y direction, you can see the numbers getting smaller, smaller, smaller. So f decreases. So in order to understand exactly how multivariable functions changes as the input varies, we will extend the notions of derivatives from Calculus 1 and Calculus 2. We will call these partial derivatives. Partial derivatives, the idea of a partial derivative is to differentiate with respect to one variable while holding all other variables constant. So you can pretend the other variables are like a constant, and then you take the derivative with respect to one variable. The partial derivatives are the rates of change with respect to each variable separately. A function f has two partial derivatives. Okay, so here we have two independent variables, then we have two partial derivatives, partial f, partial x, and partial f, partial y. The formal definitions are, so here for partial f, partial x, we consider the y is fixed. Okay, so b is fixed, and then we have the a, we have a plus change of x, and then evaluate at f minus f of ab divided by the change of x. And on the other side, partial f, partial y equals the limit change of y equal to 0. And then we have the first coordinate fixed. Okay, so this fixed. And the second coordinate, like our Calculus 1, we evaluate f of b plus change of y minus f of b over change of y. Okay, notation. The niceness notation for the partial derivatives is, so you see this symbol looks like, this is like the E, right? This symbol looks like an E, but we rotate 100 degrees, right? And you can think about this is like the 6, we take the mirror image, and this is the symbol, okay? Is the partial symbol. So partial f, partial x denotes the partial derivatives with respect to x. Partial f, partial y denotes the partial derivatives of f with respect to y. So computing partial derivatives is similar to computing the ordinary derivatives, except when we find partial f, partial x, we regard y as the constant, and we differentiate f with respect to x. To find partial f, partial y, we regard x as a constant, and we differentiate f with respect to y. So let's do some example. So here we want to find partial f, partial x, and partial f, partial y at the point 2, 1. So let's see. Okay, so partial f, partial x. We imagine y is a constant and x is the variable. Okay, so y is constant, x is the variable. Okay, then derivative of x cubed is 3x squared, derivative of x squared, but y cubed is just a constant, so it's just 2x times y cubed, and then 2y squared is a constant, so derivative of constant is 0. Okay, for partial f partial y, we view the x is a constant and we consider y is the variable. Okay, so x cubed is a constant, the derivative is 0. X squared is a constant, so just constant multiple, just leave it there. And then y cubed derivative is 3y squared. And then 2 stay here, derivative of y squared is 2y. So this is 3x squared y squared minus 4y. Now let's plug in the point to 1. So 3 times 2 squared plus 2 times 2 times 1 cubed is 1. So 2 squared is 4, 3 times 4, 12, and 4 give us 16. Do you have the same answer? So I really hope that when we go over each example, you can pause the video and then continue to work on the problem. And at the end, you play the video and check your answers. Okay, 3x squared, so 2 squared, but y is 1, okay, minus 4. Well, that's 12 minus 4, which is 8. So far, so good, everybody. Let's continue. Okay, so we have the following function. Let's find the partial derivatives. So fx is, okay, y is just a constant. Leave it there. And then chain rule. Derivative of sine xy is cosine xy, because chain rule we have u prime. Okay, so this prime is differentiates with respect to x. Okay, so that's why, well, xy with respect to x, derivative of x is 1, and then y is just like a constant, stay there. So we combine the y together, so we have y squared times cosine xy. How about fy? So fy, we consider y is the variable, x is the constant. Well, then we need product rule here because it's y times sine. So here we need product rule. So let's do it slowly. First guy prime times second guy plus first guy times second guy prime. So here the prime means differentiate with respect to y. So be careful, okay? So the derivative of y is 1, and then we have the sine xy, and then derivative of sine, chain rule, that is cosine xy, right? And then chain rule xy prime. So that is sine xy, but xy prime, y is a variable, so there is a y is 1, so we have x. So this is xy, cosine xy. So far, so good, everybody? Alright, let's continue. So next example, we have fx. So here we consider x as the variable and y and z are just constant. So let's look at the first term. Derivative of x is 1. Then the z is multiple, just stay there. 3x squared derivative of is 6x. The y stay there. And then e to the yz has no x in it. So it's just constant. So far, so good. Fy, yz has no y in it, so it's constant. Derivative is 0. And then we have 3x squared, derivative of y is 1. Oh, e to the yz. Okay, this is chain rule. E to the u derivative is e to the u times u prime, but this prime is taking the derivative with respect to y. So when we take the derivative with respect to y, then we have z. Okay, how about fz? Well, fz is, derivative of z is 1, so we have x. And then the next term, xy square y has no z in it, so the derivative is 0. Last term, we also have chain rule. E to the u derivative is u to the u times u prime. But here, this prime is differentiate with respect to z, but this guy is differentiate with respect to y. So you have to be careful. Okay, so derivative of that is y. So far, so good, everybody? Okay, let's continue. Okay, what is the geometric interpretation of a partial derivative? In Math 1200, so that's Calculus 1, derivative have a simple geometric interpretation. That is the slope of the tangent line. So partial derivatives also have a simple geometric interpretation in terms of tangent lines. So let's look at the following two pictures. We have partial x of AB. That is the slope in the positive x direction. So if we consider the curve of the intersection between the surface and the plane, y equals b. So think about this guy. We consider y is fixed. Well, y is a constant, right? So x varies. Okay, so y is fixed. So we have a plane y equals b. So this is the point AB. Then this plane is y equals b. Sorry. Let me draw it better. Okay, so it should be parallel to it. Okay, let me draw it better. Okay, so this is the intersection of the plane. Y equals b. So far, so good. Then you see the intersection is the curve. Then the slope of the tangent line to this curve at that point is the partial f partial x. So the tangent line is right here. Okay, so the slope of this line, this tangent line, is partial f partial x evaluated at its point AB. So far, so good. So we also say this is the slope in the positive x direction. Okay, let's continue. On the next picture, partial f partial y is the slope in the positive y direction. So here we have x fixed and y varies. Okay, so we consider the curve of intersection between the surface and the plane x equals a. So this is the point AB. A is right here. So x equals to a. When we intersect it, we get a curve. Okay, the plane is right here. Okay, this is the plane. And we get this curve. Then the slope of the tangent line to this curve. Okay, so let's draw it here. Okay, the slope of the tangent line to this curve at this point. Alright, so slope of this tangent line is partial f partial y at AB. So far, so good. So they represent slope of tangent lines, but in different direction. Okay, partial f partial x is in the positive x direction. Partial f partial y is in the positive y direction. So keep this pictures in mind. Let's continue. Higher order partial derivatives. Just as we have higher order derivatives of functions of one variable, we can also have higher order partial derivatives for a function of multivariables. So for second order derivatives, we can have partial f partial x, and then we take the derivative with respect to x. So that will give us the notation is partial square f over partial x squared. Okay, so this x corresponds to this x, and this x corresponds to this x. So this is fxx. Same thing as similar to partial f, partial square f, and partial y squared. So this is fyy. But partial f, partial x, then take the partial derivative with respect to y. This give us, see, this is partial square. Here, we just combine them together, become partial y, partial x. But in another notation, so this x corresponds to this x. This y corresponds to this y. So if we use this notation, we first evaluate from the right, like partial f, partial x, then like to the left, take the partial derivative with respect to y. But using this notation, you read it from the left to the right. So you take the partial derivative with respect to x and then respect to y. Okay, so what do I mean? Let me use a different color. So if you read this symbol, you evaluate from the right to the left. If you use this symbol, you evaluate from the left to the right. Okay, so similarly, this guy, you take the derivative with respect to y, and then you take another derivative with respect to x. Okay, so yx. So far, so good, everybody? So the order is kind of flipped, so it really depends on which notation we use. Okay, we mark the order of differentiation can make a difference in the mixed partial derivatives fxy and fyx. But it turns out that most of the functions we encountered has the property that f of xy equals f of yx. Okay, so here we have the theorem. So Clairaut's theorem's equality of mixed partial derivatives. Assume that f is defined on an open set D, only contains interior points of R2, and f of partial f, the second partial derivative with respect to xy and with respect to yx are continuous throughout the open set D. Then we have the mixed partials are equal at all points of D. Okay, so be careful, check the hypothesis, the conditions carefully. It must be an open set, okay, of R2, and they must be continuous. Okay, so after we satisfy those two conditions, then we have equality of mixed partial derivatives. Okay, so assuming sufficient continuity, this theorem can be extended to higher derivatives of f. For example, we can have like the third derivative. Okay, this guy means you take the derivative with respect to x, and then with respect to y, and then with respect to x. Okay, so this is all the third derivatives. So far, so good, everybody. All right. Let's do some example. Okay, so if f of xy equals y sine of xy, find all the second partial derivatives. So what is the domain? Well, y is a linear function, is continuous. The domain is everywhere. And sine is a trig function. The domain is also everywhere. So the domain is R2, right? R2 is open. Okay, and because so you kind of expect that for this example, the second partial derivatives will be the same. So let's check that. So fx equals, so we take the derivative with respect to x. Then we have done this before, right? In the previous example. See, we have done this before. So, if you don't mind, I'm gonna copy all of these here. I hope you don't mind. If you do mind, I apologize, and please watch to play back the video, okay? All right. So we have partial f partial x and partial f partial y. There are a lot of information here. Let me erase some of them. Okay. Let's see. Let's continue. So second partial derivatives fxx. So we want to take this guy and we want to differentiate with respect to x. Okay. So what do we get? Y squared is like a constant, stay there. Derivative of cosine is minus sine xy, but we have chain rule, so xy prime. So this prime, we take the derivative with respect to x. Okay, so keep that in mind. We have sine xy. Take the derivative with respect to x. Derivative of x is 1, but we still have the y. So we have minus y cubed sine xy. So far, so good, everybody. How about fyy? Well, we look at this guy and we take the derivative with respect to y. Okay, derivative of sine is cosine xy, but chain rule, we have xy prime. X just a constant, stay there. Derivative of cosine is minus sine. And because of chain rule, we also have xy prime. But because we are taking the derivative with respect to y, xy prime, the derivative of y is 1. So this guy is just x. So we have x cosine xy minus, so this we have x, and this will give another x. So that's x squared sine of xy. Is that okay? We have one x, and this gives us another x. So we have x squared. Okay. All right, let's continue. I just realized a mistake. In the previous example, we forgot this y. So that y should be here. Well, it's good that we go back to check our work. See, sometimes we miss something and, well, interesting. I have it here, but then why it disappeared? So probably when I copy down the problem, I accidentally erase it. Or I didn't copy the y. Okay. Anyway, so what do we do now? Okay, what do we do now here? Because we have y here and there, we actually need product rule. Okay, so let's erase it. And we have product rule. Well, that's the derivative of the first guy. Okay, because we took the derivative with respect to y, so we have xy prime and cosine xy plus xy times the derivative of cosine xy, which is minus sine xy times chain rule xy prime. So xy prime is x. So this is x cosine xy. This is x cosine xy. That is x, but 2 copy of x squared y sine of xy. Well, you can see the x cosine xy are the same. We can combine them together. It becomes 2x cosine xy minus x squared y sine of xy. So far, so good, everybody. Okay, how about fxy? Well, it means we take the derivative of this guy with fx with respect to y. Okay, so, well, this is a product rule. Y squared prime cosine xy plus y squared times cosine xy prime. So that's 2y cosine xy plus y squared. Derivative of cosine is minus sine xy, and then chain rule xy prime, because we're taking the derivatives back to y, xy prime is x. So far so good, everybody. Sorry, I don't have enough space, so let's not simplify it. Okay, and then f partial y x is we take the derivative of partial y with respect to x. Okay, sine xy derivative is cosine xy times xy prime. Then for the x, because you see there is a product, so we also need product rule, which is xy prime cosine xy plus xy derivative of cosine is minus sine xy times xy prime. Okay, do you see these two things are the same? We're taking the derivative with respect to x, so xy prime is just y. So this is 2y cosine xy. And then derivative of xy is y. So that's why we have minus xy squared sine xy. And can you see they are the same? So in this case, the mixed partial derivatives are equal. And yeah, because the domain are real numbers in R2, right? And both partial f partial xy and both partial f partial yx are continuous. Okay, so they're the same by the Carroll's theorem. Okay, let's continue. So all of the above concepts can be extended to functions with more variables. So let's look at this example. Let's find all the second partial derivatives. So let's see here. We have fx. Okay, so x is the variable and y and z are constants, right? So e to the minus xy, chain rule, we have e to the minus xy times x minus xy prime times cosine z. This is just like constant multiple. And derivative x is 1, so we have minus y cosine z. So far so good, everybody. And then fy is, okay, so still chain rule, e to the minus xy prime cosine z. But we take the derivative with respect to y, minus xy prime is minus x. This is minus e to the minus xy x cosine z. Well, the e to the minus xy is just a constant. Derivative of cosine is minus sine z. So far so good. Okay, let's look at the second partial derivatives. So fxx. Fxx is, well, we take the derivative of this guy with respect to x, minus e to the minus xy times chain rule minus xy prime. Copy the rest. Okay, and derivative of minus xy prime is minus y. Minus minus become positive, so e to the minus xy and y squared cosine z. Do you have the same answer? Yeah, I really hope that you can pause the video and try the problems first. Fyy, so we have minus e to the minus xy, and then chain rule minus xy prime, but this prime we're taking derivative with respect to y. X cosine z, then that is minus x. Okay, so this is minus x. That will give us e to the minus xy x squared cosine z. How about fzz? Ooh, so e to the negative e to the minus xy is just a constant multiple. Derivative of sine z is cosine z. Okay. And for the mixed partial fxy, so in this example, fxy and fyx are the same. So you can just calculate one of them. So this is, let's do this one. So we take the derivative with respect to y of fx. So there are, so we can consider this guy together, this guy together. So this is a product rule. So it's the derivative of the first guy times second guy plus first guy. Oh, first guy there is a negative times the derivative of the second guy. Okay, so this is minus e to the minus xy times minus xy prime, but because we're taking derivative with respect to x, that is minus x. Okay, so I hope you're familiar with that, because I don't have enough space here to write down every detail. So derivative of y is 1, so we have cosine z. Is that okay, everybody? So this is minus minus cancel, so e to the minus xy cosine z minus e to the minus xy cosine z. Yes. So far so good, everybody? Alright, let's continue. fxz, we take the derivative of this with respect to z, then minus e to the minus xy, y, they're just constant. The derivative of cosine is negative sine z. So far so good. fyz, we take the derivative of this guy with respect to z. Well, that is minus e to the minus xy x. Derivative of cosine z is minus sine z. So we flip the sign to positive. And that's it. So far so good. Okay. So in general, if you see the function is continuous everywhere, then you don't need to find, then you can assume the mixed partials are equal. So you don't need to find fyx, fzx, and fzy. Okay? All right. Let me put it down here as well. Okay, so this guy, we know that it also equals fyx. This guy also equals fzx. This guy also equals fzy. Okay, so that are the 9 partial derivatives. Okay, second partial derivatives. Let's continue. Conditions for differentiability. Suppose the function f has partial derivatives fx and fy defined on an open region containing AB with partial f partial x and partial f partial y continuous at AB, then f is differentiable. So differentiable implies continuity, okay? If a function is differentiable, then it is continuous. This is very similar to what we have learned in Calc 1, right? We also learned differentiable implies continuous. And here is the same idea. Okay, just generalization to multivariable. Okay, so keep in mind, if you want to check whether f is differentiable, then just find the partial derivatives, partial f partial x and partial f partial y, and check whether it is continuous. If yes, then f is differentiable. So far so good, everybody? So this is session 12.4. Have a nice day. Bye.